Good afternoon and welcome to our Terrascope webinar. Today we will be talking about air quality monitoring and assessment. My name is Jurgen Everaerts, I'm project manager of Terrascope, and today we have two speakers, Wenfu Sun and Stijn Janssen. I'll give a short introduction before we give the floor to the experts. Wenfu Sun is a PhD student at BIRA since 2022. His research focuses on machine learning for atmospheric composition and satellite trace gas retrieval, which aims to improve our understanding of air quality and environmental monitoring. Today, he will present the new surface NO2 product developed using machine learning technology. Stijn Janssen is program manager of VITO's Geo and Atmosphere Modeling team. He obtained a degree in civil engineering and received a PhD in physics in 2002. He specializes in emission and air quality monitoring to support pollution mitigation strategies from local to regional scale. As a co-chair of FAIRBOAT, he fosters harmonized air quality modeling across Europe. Stijn will present the ATMO-street, a comprehensive modeling chain designed to assess air quality from the regional scale down to street level. Now, to set the scene and get a feel for our audience, we have two polls that we want you to participate in. And the first one is, why are you exactly interested in air quality? So please have a look and provide some input on that. For some reason, I don't see any results coming in. Is there a malfunction? Okay. So there seems to be a malfunction from on my side. Your answers are the main response is that you're interested in air quality due to the impact on climate, but you're also worried about sensitive ecosystems, personal health, the impact on sensitive persons. So I think that's a very comprehensive field of interest. Now let's see if you already use actual air quality information about actual air quality levels. And again, the chat is up for you to see, but I cannot. But luckily, Evelyn will send me the results. So if Evelyn, if you can share some results with me, I would be very grateful. So most of you use national or regional environment agencies to provide information on air quality to you. The Copernicus Atmospheric Service is another important source, and then EEA and the European Space Agency follow. Okay, that's interesting. Now, let's move on to the first presentation. Wenfu, if you're ready, please go ahead. And I'm not sure if you have control.
Let me request the control.
Yeah. And you have it.
Okay. Okay. Thank you. Thank you very much, Jurgen. Okay. Good afternoon, everyone. So my name is Wenfu, and today I'm giving a talk about the surface O2 product, and the topic is about revealing the high resolution surface O2 concentration over Western Europe with machine learning.
No, I'm sorry.
It's fine.
I shouldn't touch anything.
Okay. Yeah. First of all, the surface O2 estimation is very important. In our daily life, we produce lots of the O2, such as power plants, traffic, industry, and resident activity. Also, the O2 can be emitted from the nature, such as the soil emission, lightning, and wildfires. And the O2 is a very important air component. It can impact the formation of other components, such as ozone, acid rain, PM2.5, and the pans. Meanwhile, it can, sorry, it's not a thing. We need to back to the, okay. Meanwhile, it can impact the human health directly. According to the report from European Environment Agency in 2021, there were 52,000 premature deaths due to the chronic NO2 exposure. However, the direct measurements of surface O2 over a large area is challenging because even we can have the in-situ, we can have the long-term and the reliable records of surface O2 from the in-situ monitoring station. This kind of station has a limited spatial coverage due to a sparse and uneven distribution. But still, we need to obtain the high resolution, temporary and especially continuous O2 surface O2 estimates. Because the high resolution estimate can approximate the real world NO2 distribution and let us to study the relationship between the NO2 levels and the local conditions. And with such a continuous data, we're able to analyze the NO2 dynamic and inform the effective mitigation strategy. And such detailed NO2 data can support the public health study and the urban planning and the air quality management at a finer scale. Currently, we have several ways to obtain such NO2 estimates. So the first way is physics-based atmospheric chemistry model. So this kind of model is the cornerstone in the community, and it integrates the physical and chemical process, can produce the continuous data, and can assimilate the observations. However, this kind of model usually needs lots of computation resource, especially for the high resolution estimates. And it highly depends on the accurate physical and chemical representations and the emission inventories. The second way is the retrieval from satellites or observations. The satellite observation can cover a large area, but the resolution is still relatively coarse. And we have sometimes we have the problem of the missing data because we need to remove some unqualified pixels. And the satellite observation provides the column density data. So we need to do a further conversion to get the surface NO2 with additional method and assumptions. And in recent years, the machine learning model is becoming more and more popular and has been widely used in many disciplines, including the air quality study. And such machine learning model benefits from the rapid developments in computing power and the increased availability of the big data. And this is a data-driven approach, so it does not require explicit coding of a physical and chemical process. And it has a strong ability to integrate different types of data set and very efficient for high-resolution estimates. And this is the framework. This is the framework of the model that we use to estimate the surface NO2. So don't be scared, I will not go into the details to these slides. And you just you just need to know that this model, the name is Benki. So we constructed based on the tree-based machine learning model, and it can provide a 1-point estimate and two prediction intervals, and and these intervals can tell us the estimates uncertainty, and then also we use the assemble strategy to reduce the modeling randomness to make the model performance more stable. And here is the basic idea of how we use the machine learning to infer the surface NO2. First, we use the machine learning to learn the relationship between the major surface NO2 and different types of data sets over the regions where monitoring stations are available. After that, we apply this machine learning model to the new area where the monitoring stations are not available. And with those input data sets, we can get the surface NO2 value for this region. And in our study, we have used 29 predictors in total, such as and these predictors comes from different types of data sets, such as satellites, meteorology, emissions, and the land. And the training data set is from the surface NO2 measurements from the in-situ stations. And after training, we use the tenfold space-based cross-validation to evaluate the model performance. And the result shows the model is reliable as the point estimates has a good alignment with ground measurements, and its prediction interval meets give a right coverage rate. And in the right-hand side, you can see this banking model can provide us the spatial distribution of NO2 and also can enable us to know the time series of NO2 variation for a specific location. And here is the surface NO2 product. This is a demonstration of the surface NO2 distribution. And this is the average distribution calculated from 2018 May to 2021 December, and for the Western Europe. And the estimates over the grid areas require further validation. So today we just focus on this highlighted area. And as you can see, we have a very the structure of a NO2 map is very obvious and very fine. And we can zoom into some regions to see a more detailed distribution of NO2 in, such as for Paris and northern Belgium and Netherlands and Western Germany. And the WHO limit here is 25 milligram per cubic meter. So the corresponding color is the orange. So in this map, if you see the region with such color with the orange or red, this means this area is under the NO2 pollution. And here is the example about the NO2 daily variation. So we take the example for COVID time in 2020, and we take the same months in 2019 as a reference. And here there are two types of data. One is from our surface NO2, another is from the CAMS model. So CAMS, is the state-of-the-art physical model, and we also use the CAMS as a reference. And you can see in the 2020 the COVID time, there's a very significant decrease of NO2 in this period compared with the 2019, and their difference almost disappeared at the end of the April. So which was also the end period of the city lockdown. And here we can use the surface NO2 product to calculate the NO2 exposure. And in our study, we calculate the exposure as the frequency of NO2 pollution days from 2018 May to 2021 December. And in the left-hand side is a determined exposure, which is about, in this case, the surface NO2, the point estimate is above the WHO limit. And in the right-hand side is the potential exposure. Because in the machine learning model, we have considered the uncertainty caused by the data itself. So here we consider further consider the uncertainty impacts on the exposure study. So we have another scenario when the point estimate is below the WHO limit, but the expected range still cross over this limits. And this means we still have the possibility to have the NO2 pollution. So you can see for the determined exposure, this is mainly distributed in the urban, especially the central part in the urban and the industrial area. And for the potential exposure, the level is the high value is mainly at the suburban region and some rural areas. And now the surface NO2 product can be accessed via the Terrascope portal. And here, this is the example for the Brussels. And this is the yearly average surface NO2 for 2023. And because the surface NO2 product has a very high resolution, the 1 kilometer resolution. And so you can see it has a good correlation with the city layout. And for example, along this main road, you can see the NO2 value is very high because this place has a very busy traffic. And in the right-hand side, we take the NO2 column density from satellite observation as a comparison. Because the satellite observation still have a relatively coarse resolution, so it's very hard to see the NO2 distribution, the NO2 spatial gradients in such urban scale. And here is this is the surface, this is the one-day case for both surface NO2 and the satellite data. And you can see now the surface NO2 product can covers a very large area and can provide the NO2 information over the continents of the Western Europe for every place. But in the right-hand side, you can see because we need to remove some unqualified pixels. So the missing data, this issue sometimes is inevitable, and we lost the signal for some locations. But we still able to see we can still able to know the NO2 situation over those places. Okay, let's go to the conclusion. So in this talk, we know the high resolution estimation of surface NO2 is very important, and we have developed a machine learning model to estimate the daily surface NO2 as a 1 kilometer resolution. And this product can capture the spatial and temporal variation in surface NO2, and also supports the calculation of the NO2 health exposure, including the potential exposure. And now this data set can be accessed via the Terrascope portal. And the paper for this work has been published in October. So if you are interested in the details, please read this paper. And this paper is open access in the JGR atmospheres. And this slide is about some preliminary plans for the next year. So in the next year, we will aid on certain for the banking model for the surface NO2 products. We will add uncertainty information in the future updates, and we are thinking of to use this model for a large area, and this model will be validated twice a year, and we will keep this iterating with the most recent data. Another is about the news of the new product. It's a 3D NO2 product, which might be published in the next year. So this product is developed using the neural network-based model. With the 3D NO2 product, we are able to capture the NO2 transport in the higher layers. As you can see in the right-hand side, this is a demonstration of this product for 4 days. And in the surface layer, so which is the top part, it's very hard to see the NO2 transport pattern. But when you look up from the 50 meter, 250, and 500 and 1,000 meter, and you can see more and more obvious NO2 transport patterns. And this can help us to analyze the NO2 pollution with the perspective for the inter-region transport. And this product is also at a high resolution. So in the future, we can provide these high resolution profiles for satellites retrieval. Okay, so this is my part. And now I give the floor to Stijn. Thank you very much.
Okay, Wenfu, thank you for this very interesting presentation. For the audience, this may have raised some questions. We will answer them at the end of the session, but you can already post them in the Q&A. Now, to move on and give another view of the situation, Stijn will take over.
Yes, thank you, Jurgen. So my name is Stijn Janssen. I'm trying to get control over the screen. Yeah, here we are. So yeah, in the next 15 minutes, I will give a brief overview of the ATMOSYS modeling system, which is actually a toolbox that we have developed to support the implementation of the Air Quality Directive. And I give this presentation also on behalf of the entire team at VITO working on this modeling tools. Maybe to start, I'm not sure if you're aware of, but very recently, actually a few weeks ago, late October, a new air quality directive was published by the European Commission. It took quite some time before the final texts were agreed upon by the different member states and the European Parliament and the European Commission, because everybody wants to have a say in the final legal text as that goes. But okay, eventually the new directive is there, and what is very striking is that the role of air quality modeling is really much more prominent, embedded in the legal texts. And so this is, I think, relevant still. Yeah. Over the last couple of years, we've been actually working on developing a modeling toolbox to support the implementation of the directive. And that comes under what we call the umbrella of the ATMOSYS toolbox. And basically, it comprises of 3 different pillars, which try to fill in different parts of this air quality directive. First of all, there is what we call the OPAC tool, which deals with operational aspects of air quality, both forecasting and real-time mapping. Then we have a pillar related to high-resolution mapping, which we call ATMO-street. I will say a few more words about that in a minute. And then finally, we have developed a kind of an planning toolbox that supports the development of urban air quality plans under the umbrella of ATMO plan. We don't do this. Sorry, I have a bit of a problem with the control. We didn't do all the developments ourselves. This was in close collaboration, first of all, with people here in Belgium, in the environment, the Flemish Environment Agency, and IRSEL, who heavily contributed to the development. Also, we had support from the European Commission under the LIFE program. And then over the last 10 years, we've also applied parts of this toolbox in other EU member states. And you see a few of these partners in Slovakia, in Poland, in Croatia, in Ireland, in Hungary. we also contributed to the development and actually the deployment of these tools in the respective member states. So let's now switch to ATMO-street, which is actually our modeling system for high-resolution air quality mapping. And actually, the toolbox is designed in order to really cover all the relevant aspects of air pollution from the regional down to the local scale. So we first start with a mapping algorithm that covers what we call the national or the regional scale. Then we try to zoom in on the most relevant features that happen at the urban scale. And then finally go down to what we call the street level scale in order to, especially for pollutants like NO2 or black carbon, capture the essence of what's really happening in the so-called street canyon situations. When we set up this modeling system, of course, we have to rely on a wide variety of input data sets. Mainly, we start out of actual measurements collected in a monitoring network, but we also, of course, rely on various emission inputs. Can be residential emissions, can be traffic emissions, which are obviously very important. Also, industrial emissions, mainly coming from large stacks, but also more diffuse emissions on the industrial sites. And then finally, we combine that also with building information, especially to take into account the so-called street canyon effects, methodological data, of course. Then this all goes into the modeling system in order to produce these countrywide maps, which eventually can go down to street level scale. So I will not go into the very technical details of the different types of models that we use, but basically it's a coupled model chain. So we start with a rather core scale model, which covers what we call the regional scale, which provides us with concentration fields at the resolution of 3 by 3 kilometers. Then we couple that to IFDM, which is a Gaussian plume model, which gives us what we call the open street concentration. So there you see in the middle, you see already the impact of highways. And then we couple that in a final phase with a street canyon module, which really gives us the street canyon increments down to a resolution of about 10 by 10 meters, mainly relevant for the urban environment. Yeah. So, okay, before we continue, maybe it's time for another vote, see if everybody's still awake. And so, as I said here, we try to cover the different spatial scales, but yeah, we're curious. Are you really interested in all these different spatial details? And maybe, yeah, you have a certain preference, and it would be nice to have your opinion. Here. So Evelyn, you have to help me out a bit. Not sure where I can see the feedback. So I think, yeah, the most relevant scales are the urban scale, followed by the street level scale, the regional, and also the global scale. So the majority is voting for the urban scale. So that's good to know. Thank you for that feedback. So let's move on. So, okay, here I gave the example for Ireland and Dublin because we've just finished a large project for the Irish EPA, but we did similar exercises also in other parts of Europe, as I said before. So here you see a few examples, one for Warsaw in Poland and another one for Budapest, where the same type of maps have been produced in cooperation with the local environment agencies or meteorological offices in the respective countries. Okay, so now of course you can question, okay, you make nice maps, but how good are these? How valid are these modeled results? And then we were very lucky, as some of you may recall, in Belgium that there was a very big citizen science campaign. It was launched under the name Curieuze Neuzen, and actually more than 20,000 people participated via the collection of actual air quality samplers air quality measurements via so-called passive samplers. So here you see a picture of such a passive sampler which was detached to a board that people could put in front of their house. And so we were able to connect collectively over one particular month, more than 20,000 sampling data over the entire region. Here you see an extract of the map. So here you see the amount of data that was collected during this citizen science experiment. And so we have, with this data set, really a tremendous amount of information available about the spatial variability of, in this case, NO2 patterns over the region of Flanders, which provided us as modelers with a very interesting data set to further validate our modeling chain. And so this is actually also published in a paper in 22 in an atmospheric environment, where we actually used this curieuze neuse data set to validate the ATMO-street model chain. So you see just two extracts out of this paper. For the full details, I can refer to the full article. But here you see in the left a validation between or a comparison between measurements, the 20,000 measurements, monthly means over the region, compared to what the modeling is telling. Of course, there is still some spread in the data set, but on average, we were quite happy with this validation. Also taking into account that the data itself was collected in the citizen science campaign, which also brings some extra uncertainties in the measurements. But at least this gives quite some confidence in the output. The other picture that you see is a semi-variogram, which is actually a measure or an indicator that reflects the spatial heterogeneity or the spatial variability within this data set. And as you can see, the low resolution model, so really the regional model, which was covered by the Rio model or even the Rio IFDM model, you can see that these regional models lack the fine scale details which are picked up in this sampling campaign, and are not able to represent or to reproduce the spatial variability. And so you really need the full complexity or the full details which are embedded in the ATMO-street to represent this the blue dot or the blue line, which is actually the variability in the measurements or seen in the measurements. And even by making use of this citizen science campaign, we were able to improve our original ATMO-street model, which is depicted in green, in order to even better represent the spatial variability that was seen in this particular experiment. Okay, so as a final part of my presentation, I would like to say a few words about the application of this type of maps, because of course, making an assessment map and say, okay, this is where the hotspots are, is of course one thing in the air quality management process. Of course, people want to also know, okay, what can I do about these hotspots? And then we enter in what we call the whole planning phase. And just one example to demonstrate what, once you have such a model in place, what you can do is run all kinds of policy scenarios. And one scenario that somehow speaks for itself, or that got quite some attention some time ago, was a model simulation that we performed for the city of Antwerp back in 2020, where we were asked to assess the impact of banning all the diesel cars in the city of Antwerp. So at that time, the air pollution was given by this map here on the left, and people asked us, okay, if we now would ban all the diesel cars in the city, what would be the impact? With this type of modeling systems, you really can switch off certain emissions for certain vehicle categories, and then the model system can tell you, okay, this is the improvement you can gain under certain policy conditions. Actually, this debate is still going on, and for those who have followed the news in Belgium, we know that these days there is quite a debate about the effectiveness of the low emission zone, and whether or not the city of Ghent will maintain a low emission zone or not, or if we will strengthen certain conditions or not. Actually, on top of this ATMO-street tool, we also developed what we call the ATMO plan. system. It's an online web application, an online support tool where people can actually design policy scenarios themselves. And this is just an example where actually city authorities or people in the administration can design scenarios themselves. And so this is an example for Aarschot where you can then draw a layout for a low emission zone in the city center. You can define how the low emission zone should look like. So for example, you ban diesel cars or diesel cars of a certain category. In this case, maybe only diesel cars of the Euro type number 4. And then the system, you can launch the calculation, and then the system feeds back the impact of your scenario that you have designed. So just to demonstrate that, okay, you have the map, you have the model, we can validate the results of the model, but once you have the model, you can also apply it then in a policy context. Voila, so this brings me to the end of my presentation. So in conclusion, we've seen that over the last decade, let's say, air quality models have really become much more mature, represent much better what is seen in the atmosphere. This is also somehow picked up by the legislative authorities, and the new air quality directive now much more also relies on air quality modeling to support policy making in the whole of Europe. And with the ATMOSYS toolbox, we have actually a system in place that supports the implementation of the directive on different aspects. Today, I've mainly focused on the assessment and the planning part, but with the system, we also have something on forecasting to run operational forecast and to say something about source apportionment, but that will be for another presentation. So I would like to leave it here. Jurgen, back to you.
Thank you, Stijn, for this insights. We now have time for questions. We've already had a few coming in for Wenfu, so let's take those first. But in the meantime, everybody that now has questions about the finer scales can post them in the Q&A. Let's go. A question, the first question is, if I understand correctly, you are using Sentinel-5P and ground sampling as 2 inputs and then determine NO2 concentrations via your machine learning model. Are you currently, or will you in the near future, include local climate, local weather condition, air turbulence and topography information to detail your mapping and monitoring results further?
Okay. Yeah, I have seen this question. So yeah, thank you. In our model, we have used the Sentinel-5P the TROPOMI data set as a 1 input, and the ground sampling from the NO2, the ground measurement from NO2 is used as a training target, and we also have used the meteorology data and also the land elevation data as the input. So indeed, we have used we have already used this weather condition. We have this weather condition as a factors as a predictors. This data, the meteorology data is mainly derived from the EI5 and the EI5 land. So the resolution is 25 kilometer and 9 kilometer, but it's still relatively coarse. Yes, in the future, if we have some very fine resolution meteorology data, we can think of to use that to improve the model better. So yeah, to detail the mapping. Yeah, thank you for the question.
Okay, next question. As Sentinel-5P is sun-synchronous in a polar orbit, how do you deal with the time resolution? Is this really daily data, or is it rather an hour estimation of that time when the satellite passes over?
Yeah, okay, this is a good question. So in our work, we provide the daily average surface NO2. So it's not the NO2 for the satellite overpass time. It's a daily average, and we know that the satellites, the overpass time of the Sentinel-5P is a 13:30 in the afternoon. So, but here we use the satellites as like the background, as one predictor, and it can provides the model till background information, till the general NO2 level for today. So so for the machine learning model, it's not necessarily to just not it's not necessarily to only estimate the surface NO2 data for the satellite overpass time, but we can use another way to make the satellite just provide a background information. So yeah, so that is how, and the training data, and here we use the training data is the 24-hour average from the monitoring station. So the model output is the 24-hour daily average.
All right. Following up on that question from Erwin Wolters, who was part of the Terrascope early days and with the atmospheric modeling. So I'm happy to see you again. For the days with missing Sentinel-5P daily data, the machine learning is driven solely by the ground stations and auxiliary data, I assume. To what extent does this increase the prediction uncertainty?
Sorry, can I see the
so if you don't have satellites observations,
for the days with the missing the information is driven solely by the ground. Okay, yeah. In our model, we during the training phase, we didn't during the training phase and also the implementing phase, we didn't filter out any satellite pixels. We keep them all, and but we also use a lot of as I introduced before, we have 29 predictors in total, and the satellite here is used as a one predictor. And during the research, we found that when the satellites satellite data has a much of noise, the model will transfer the dependence to other features to maintain the performance. So yeah, this is one interesting thing that we found during this research. And you are welcome to read the paper. And we have a section to discuss this. Yeah, thank you.
All right. Following question: can you see the impact of large individual NO2 emission sources, such as power plants, steel production plants, and so forth, using your approach? For example, plumes of overpower plants or traces of NO2 pollution change depending on meteorology?
Yeah, this is also a good question, but it is more about the application of our surface NO2 products, and we would like to do a further check to see if our model, if our data can, if you can find such a large NO2 emission from such data, and we will do this later, and you have also mentioned the plumes over the power plants. I think usually this kind of scenarios happens not only at the ground, not at a surface layer. It happens like in the 50 meters high. So, and this is the reason that we are going to develop the 3D NO2 products, because usually the NO2 transport and NO2 pollutants is more visible in the higher layers. At the surface layer, it's very hard to see such a transport pattern. And you also see the NO2 and NO2 pollution change depend on the meteorology. Yes, and we have we have also seen the NO2 the meteorology play a very important role in the NO2 pollution level, and in the paper we have done some analysis about the feature importance, and we have seen the meteorology has a very strong impact on the surface NO2 level. So yeah. So again, if there are many details are in the paper, and if you have more question, you can contact me after the seminar.
Okay.
Thanks.
Thank you, Wenfu. I'll give you some time to breathe. I have a question for Stijn. Have you already encountered the cases where policymakers instrumentalized such digital science-driven tools to actually enforce the regulation compliance, like those under the new air quality standard? And extending that, does your model also include different scenarios for weather conditions and wind patterns?
Yeah, maybe I answered the last question first. So indeed, and I didn't put a lot of attention there, but actually the model runs on an hour-by-hour basis. So if we do a simulation for a particular year, for example 2022 or 23 as a base case, we run all the individual hours and we take into account actually the meteorology, which is, as Wenfu already said, a very important driver for air pollution. We take the meteorology for that particular hour in order to produce an annual average map. But of course, based on this hourly time series, we can also derive other statistics like exceedances above certain thresholds, etc. Then to come back to the first question on the policy relevance of these tools, I think as we speak, we are now using this ATMO-street model to support the Flemish government in their air quality plan that they have to develop for the European Commission. So the model itself is used together with colleagues in the Flemish Environment Agency to prepare the actual policy plan for Flanders. Then the translation in this web-based tool, this ATMO plan system that is used to, or is developed for end users to develop their own plans. There, I think we have a very nice example now actually in Slovakia, where the system is used by the national authorities in order to provide a software system to their consultants. So all the consultants in Slovakia actually use ATMO plan to develop their local air quality plans or environmental impact assessments of all the projects now ongoing in Slovakia, and to assess the impact of certain development plans, be it industrial, be it transport or construction plans, on air quality. So exactly, the tools are used also to support practical implementation of the directive. And then to come back on the wildcards, that's I think it's a good question, because we're bound to the major pollutants under the air quality directive, which is NO2, particulate matter, and so on. But especially also in Eastern Europe, benzoaperine is a very relevant pollutant because it's emitted via coal burning or wood burning, which is quite abundant in Central and Eastern Europe. And so especially for this type of countries, in Hungary, in Poland, in Slovakia, there was a specific request to add other pollutants like benzoaperine, and then they can use that via this wildcard functionality.
Okay, Stijn, but following up, with respect to the ATMO-street and ATMO plan, will the increased inclusion of urban dynamic climate parameters modeling and simulation like URCLIM be able to provide a more locally exact 4D prediction?
That's a good question. Maybe with respect to climate, the same model can be used also to make long-term projections. So actually, we're just starting another project for the Flemish Environment Agency to make an impact assessment of future climates, and then we look towards 2050, and we will take on board climate projections for 2050 and use these data sets as input for ATMO-street in order to assess the impact of changing climate on air pollution. So there the model is capable to deal with this kind of policy questions. On the other hand, if you really want to go to a very detailed 3D understanding of the situation, you have to switch, because you didn't go into too much detail, but in the end, it's still a kind of a 2D or a 2.5D representation of the atmosphere. So we have a ground layer, and in the canyons, we make a street canyon increment. If you really want to go to a full 3D understanding of the atmosphere, you have to switch to CFD, computational fluid dynamics. And that's actually also a type of model that we're running at VITO in the ATMOSYS team. I didn't say anything about that, but yeah, then you have to switch to a more localized, even what we call the micro scale. Today, that's not feasible for the entire region or the entire country, but at city scale, actually, we are now wrapping up a project for the city of Antwerp, where we do the full city of Antwerp at meter resolution with OpenFOAM, which is a computational fluid dynamics modeling system, and that actually takes into account all the things like urban dynamics, boundary layer, turbulence, etc.
Right, Stijn, thank you. And then another question for Wenfu. Can your machine learning model be used to determine the effect of emission reductions, like the shift from conventional to electric vehicles, on the NO2 concentration? What is the runtime of the model, and is the model available?
Okay. Yes. Thank you for this question. It's a really good question. So it's about how our predictor can provide the NO2 dynamic, and here is about so in our model, I still need to say the satellite observation is a very important one, to provide us the NO2 dynamic NO2 variations. So yeah, this model can we haven't checked if the model can detect the vehicle type transfer, but we have already seen just as I showed before, we have already seen that there's a significant decrease during the COVID time, and we find that in this part the satellite has done a great job to help the model to capture that. So we will do the further check that. Thank you very much.
Okay, I think we need to conclude the Q&A. We still have a small section about possible synergies between our two presentations. Maybe Stijn, you can say something about that.
Yeah, okay, the full session was filled with Q&A, which is fine, but okay, we even thought about, okay, what are potential synergies, where do we further want to focus on in a collaboration between BIRA and VITO. As you've seen, and as I said, the regional background is really a key driver also, even for these fine scale models as ATMO-street. And we really believe that also Earth observation data or the methods developed by the colleagues in BIRA can be used to further improve that part. It was already mentioned in the Q&A that, okay, also Earth observation can potentially help in identify unknown sources, because in our deterministic approach, we always rely on the emissions as they're known in the emission inventories. But I think one of the potential strengths of Earth observation is that you really can also detect from above what is actually missing in the emission inventories. And we know shipping, for example, is a difficult sector, some industrial sources as well. And then, okay, we've now mainly speaking about what we call the data-rich regions. So we have a lot of information available in Belgium, in the Netherlands. But okay, what in what we call the data-poor regions, for example, we know that when we go to East and Central and East Europe, there is far less data available. What if we go to Africa, to South America? So also there, I think there is potential for Earth observation-based technologies to further strengthen the air quality assessment.
Okay.
These were just some thoughts, but yeah.
All right. Wenfu, any comments on that?
Nice.
How much effort would it take to set up a similar analysis for instance, Africa? Or what are the difficulties when doing so?
So you mean for this in the data pro regions?
Yeah.
Yeah, it's I need to say the training data is very important for the machine learning model, and the machine learning model has a very high requirements of the data abundance. So for the application for the other areas with a very few observations, the good way is to integrate to combine the machine learning model with the traditional physics-based model, and to make the model to learn some physical knowledges, and then use the observation data to make a fine tune of the machine learning model to fit the situation of America, of Africa and Asia and other place. And this is what we are also trying to investigate. Yeah, because we also know, yeah, because that's the limitation of the machine learning model is also very evident.
Right. Okay. So there's still work for time and possibilities for new developments, and that's ideal. So it's close to 5 o'clock. We're going to conclude this webinar. Know that we have a use case published on our website, terrascope.be, which is devoted to the new service product developed by Bira. If you're interested, you can also subscribe to our Terrascope newsletter. And if you want to contact us, please use the info@terrascope.be. Even if you want to contact our presenters, we will happily pass on any of your questions to them. Thank you again, Wenfu and Stijn, for your presentation. Thank all of you for attending and for asking questions. And I hope to see you again in one of our next webinars. Good night.